Good afternoon. I hope you have your lunch and you're ready for 45 minutes to learn more about real-time digital twins. I'm Bill Bain, and I'm the founder of ScaleOut software and also its CEO. We're going to talk today about how to integrate data parallel analytics with stream processing using the digital twin model. So I'm the founder, as I say, and I've worked in parallel computing for several decades now, more than I'd like to count. Our company, ScaleOut Software, develops in-memory data grids for both scaling application performance with data storage, in-memory data storage, and also for operational intelligence to analyze by analyzing live data with in-memory computing. So the agenda for today is to first of all look at some of the challenges for stream processing when tackling large numbers of data sources. Then look at the real-time digital twin software model and some of its applications and examples, and see how it helps solve this problem of tracking telemetry from large numbers of data sources. We'll look at a code sample and give a demo of that code sample. We'll also look at how an in-memory data grid can be used to host real-time digital twins and how they play an important role in aggregate analytics. And then we'll look finally at how in-memory data grids can implement aggregate analytics by integrating with digital twins. So here are some of the goals for tracking large numbers of data sources. You might think about a smart cities application with sensors all over a city and a cloud service tracking that telemetry coming in from thousands of data sources, such as sound meters at intersections, traffic lights, gas sensors, and many others. And the trick here is, how do you predict emerging issues? How do you see where they're occurring, how they're moving, and how do you react to them with maximum situational awareness in real time? And so to do that, you have these challenges in stream processing for how do you track state for each data source so that you can introspect on what the telemetry from the data source is telling you. And how do you scale the cloud service to handle thousands or hundreds of thousands of data sources? And then how do you aggregate all this information, not offline, but in real time, so that you can maximize situational awareness? Here's an example that we've looked at in fleet telematics. You probably know that most trucks, 18-wheelers on highways, have what are called sensor hubs that are collecting telemetry from throughout the vehicle and then transmitting it wirelessly to a cloud service for analysis. These sensors have information that includes their position, the lateral acceleration, the speed, engine parameters, and cargo parameters. So with this telemetry, the dispatchers that are running the telematic system want to be able to analyze the several issues. Like, they want to be able to predict whether or not there's going to be an issue with either the vehicle or with its cargo. They want to look to see if the vehicle is where it should be and whether it's on time or late. They want to see if the driver is driving erratically or appears to be lost or fatigued. And importantly, they want to determine if a driver is driving past the legally allowed time, because that can create legal issues for the company. So there's several issues that need to be tracked, and they all require tracking state information about each individual truck. It's not enough just to look at aggregate statistics coming through a streaming pipeline. It's important to actually keep information about each particular truck and then be able to aggregate key parameters to determine whether or not there are overall issues with the fleet and issues that need to be analyzed immediately and handled immediately. So a typical streaming analytics platform typically is pipeline oriented. Examples are Apache Storm, Flink, and Beam, and some commercial products. They either use a direct pipeline or a directed graph of processing stages. And this can create some complexity challenges when handling large numbers of data sources, because it requires the application to pick out the messages from a given data source, correlate them, and then map that into information known about that data source in order to introspect on what that data source is saying. So these platforms, these kinds of streaming platforms, are really designed more to pick out interesting changes in the telemetry, but not to necessarily introspect on the behavior of the data source and why that data source is behaving the way it is. These pipelines also can create performance challenges in mapping this processing and data storage to a system for execution and scaling that, because bottlenecks can appear in the pipeline. Pipeline stages might have to be rebalanced in order to achieve the scalable speed up and to avoid network overheads. And the problem of network overheads can be very high because of the fact that to keep contextual information about each data source typically will require an external data store, like a blob store, a database, or a distributed cache. And when telemetry comes in, the processing stage has to go retrieve that state, analyze the telemetry in the context of that state, and then perhaps update that state if a change occurs with the data source. This requires network access outside of the computational servers that implement the stream processing pipeline and can create network bottlenecks, as you see here in this picture. So the problem with bottlenecks in network access to a data store is that it impacts the scalable throughput of the entire system. So you can see a graph here on the right, which is not a streaming analytics application, it's a financial services application, but it illustrates the same point, which is that when data is being accessed randomly over the network, instead of being held immediately in the processing servers which are doing the stream processing, or in the case of this graph, the financial services computation, then the scalable throughput is impaired. In fact, it falls off dramatically, as you see in the blue line. The red line shows the kind of linearly scalable throughput that a system needs to achieve in order to handle a large workload and a growing workload in case of stream processing, to handle many messages per second without creating delays in responding to the data sources. So how do people solve this problem? One of the techniques people use when they know they're trying to track individual data sources and they have thousands of data sources is they build an ad hoc combination of services, today usually in the cloud, that will put together the functionality that's needed to track these data sources, and instead of using formal APIs that we've seen in the pipelined approaches. So for example, they might use a web service to collect telemetry in the fleet telematics case to receive messages from the trucks, and then use a database service to host information about those trucks. They might also use an in-memory data grid to snapshot the telemetry until they can process it. They also will have application servers behind those web servers that are processing these messages, updating the database, and retrieving and storing information in a cache. And then the job of these application servers is to push interesting telemetry and computed values out to a data lake, to an analytics service for processing. And a typical one would, of course, be Spark today. And the problem with using an offline analytics service is that it can create delays. So you can see here what happens when data is pushed through a data lake for offline analysis. This typically incurs delays that range from minutes or even hours, as the batch processing of the offline system, which can handle large amounts of data, but is not intended for working with live, fast-changing data, it runs in order to provide the visualization of the changes in the telemetry and the behavior of the data sources, which are important for the dispatchers in the fleet telematics example. So the problem then is that the visualization might be an hour delayed from the actual changes in telemetry, which means that offline data analytics can only be used for handling big strategic issues like fuel efficiency for a fleet, issues about rerouting a fleet of trucks in order to optimize the cost and the delivery times. But it's not good for real-time processing and handling emerging issues that occur within seconds and need to be dealt with within seconds. So that's where the real-time digital twin model comes in. This is a new software technique for tracking large numbers of data sources, and it focuses on state tracking instead of event processing. So it's refactoring the streaming pipeline around the state information about the data source. And what you can see here is it's keeping state information for each data source, typically within an in-memory data grid. We'll talk about that in a little bit. And then it refactors the pipeline processing code into one set of logic that is run for each message or set of messages that come in from a given data source. So the real-time digital twin model is automatically going to correlate telemetry from each data source, hand it to this application-defined processing code, and let that code update the state of that data source in the in-memory data grid. So this provides a software framework, an orchestration framework for application logic, which could be written in C# or Java, or be implemented with a rules engine, or it could encapsulate machine learning algorithms, neural network within the digital twin model. It also provides the basis for data parallel analysis or aggregate analysis across all of the digital twin instances to find emerging patterns and trends and do this in real time without having to push the data out to a data lake for offline batch processing. So let's look a little deeper into the anatomy of a real-time digital twin. A real-time digital twin describes how to process messages. This is a model is implemented by the application developer, in which the developer describes how messages from a given data source are to be processed and how state information is to be tracked. And it comprises two components. First is a state object definition defined as a subclass of a base class provided by the platform, in which the properties for that data source and the derived properties that can be computed by message processing are stored. And it's made immediately available to an application-defined method we call here a process messages method, which implements the application-specific logic that analyzes incoming messages either one at a time or in groups, and then responds or commands the device or creates alerts. And so what these two work in concert, the process messages code retrieves the state object data, looks at the messages, updates the state object as necessary, sends out commands or alerts, and then waits for another set of messages to come in from that particular data source, which means the application-specific logic is only worried about handling telemetry from a given data source. And this simplifies the problem dramatically for the application developer. It also means all of the orchestration and the correlation of messages can be handled by the platform instead of by the application. It also means that any code that's useful for this particular application could be implemented by the process messages method. In particular, as I mentioned, it could be just a plain old Java or C# method, or it could be a rules engine, or it could be a neural network. So digital twins have been used in other contexts for many years, going back to 2002, when they were originally described by Michael Greaves at the University of Michigan for product lifecycle management. You can think of the problem of building components for a jet or for a large factory, valves, controllers, generators, and so forth. And what you want to be able to do is have a model of those physical components, and then as telemetry comes in from the field, you will help you to design the next generation by understanding where the weak points are and how you might redesign. So they've also been used extensively in the IoT platforms. For example, AWS Device Shadow to track the parameters of a device. Also, Azure has a similar device twin. And in addition, Microsoft Azure Cloud has a digital twin model. So the other two are device twins, they're called. A digital twin model, which provides a spatial graph for describing buildings, spaces, devices, and people, and modeling the hierarchical relationships between them so that a hierarchical view of a very complex set of entities in the real world can be tracked with a digital twin model. What we're talking about today is using real-time digital twins to focus on analyzing incoming telemetry from a large population of data sources, which typically they're large groups of the same type of data source, like a fleet of trucks, but it could also be the drivers could be modeled as a separate set of digital twins from the physical trucks themselves, so that you can track different issues in telemetry from the two types of entities. You might also see this, we'll see a picture in a minute, of doing this for an airline, tracking its passengers and also its planes. So the Digital Twin Consortium came up with a definition for digital twins, and you can see it here in the box. And we're speaking about the part of the model which is described in yellow here, capturing real-world behavior for analytics and learning. So some of the advantages of using a real-time digital twin model is that they, first of all, they provide a simple and flexible way to track a large number of data sources. They're simplifying the programming problem by refactoring it such that the concern of the application developer is just on introspecting on the telemetry from a single data source, and then making that orthogonal to the problem of doing aggregate analytics. So they allow for deep introspection because they provide state about that data source as a first-class citizen of the model. So instead of the application having to go cobble together a state mechanism, the state for that data source is automatically held in memory for fast access and made available to the application-specific code. And this enables fast responses, commands, and alerts and typically measured in 1 to 3 milliseconds because of the fact that the data about the data source and the derived state is immediately available. It also allows the message processing to transparently scale because it can be mapped to an in-memory data grid where an object in the grid is hosting the state data for a given data source, and then servers can just be added to the grid to handle more and more digital twin objects. And lastly, it provides a basis for aggregate analytics, which is what we're going to be talking about today. So there are many applications for this real-time digital twin approach to stream processing. They typically fall under the heading of real-time intelligent monitoring, where we're trying to maximize situational awareness in a live system. We've seen 2 examples, the smart cities example, and you can imagine all the IoT devices that are feeding telemetry to the cloud service in a smart cities environment. Also, fleet telematics we looked at, and logistics problems. We'll take a look at one for hospitals in a few minutes. Contact tracing for COVID, security and disaster recovery, and we'll look at a demo of security tracking in just a minute for a power grid. Health device tracking, making recommendations to e-commerce shoppers by watching the types of products they're looking for and trying to understand what their needs are. And also many applications in financial services, such as fraud detection for wire transfers, and countless others. Anytime there's a large population of entities which need to be tracked in real time and issues need to be surfaced and strategically handled, then real-time digital twins can be useful. This picture depicts an airline which is tracking flights and tracking passengers so that it can offer passengers reroutes based on weather changes, do so in the moment even while they're flying through mobile devices so that we can give a better quality of experience to the airline passenger. That's yet another example of real-time digital twins, and it shows the use of 2 types of digital twins running on the same platform. So here's an example of contact tracing for corporations or companies. The problem of contact tracing has been challenging for the public because of privacy issues and reluctance for adoption. But real-time digital twins can help companies track employee contacts with numerous advantages. Most important is it can immediately identify microclusters of exposures so that they can be contained before they spread. So companies need these fast notifications, and they can take advantage of their knowledge of work groups and interactions between work groups, as you see in the picture. And employees can use the company calendar, or they can explicitly notify the company about meetings and who in which group they're meeting with that's outside of their normal work group. And this enables the company to implement policies when an exposure is identified and to quickly react. So here's how this contact tracing application might be implemented. A real-time digital twin instance can be created for every employee in the company. So if you have a 30,000 employee company, you would have 30,000 digital twins. And then a mobile app can be used, and we created one to demonstrate how this could be done, in which the employee signals the company whenever the employee has an interaction outside the employee's group, or perhaps during business travel, noting the airline and flight and seat number, or taking an Uber and noting the date and time and location of that, so that later if this employee or another employee tests positive, they can use that mobile app to also notify their digital twin that this positive test has occurred. Now, looking at the lower diagram there, you can see that this will trigger a chain reaction of messages between digital twins as they follow the network of contacts that have been maintained by the digital twin. So each digital twin will maintain these contacts and then notify the digital twins for those contacts in a network fashion after this exposure has been notified. And then all the digital twins that are signaled can then also send a signal back to the mobile device to notify all the affected employees, who then would need to obviously to isolate and to remain away from the company until their exposure period has ended. So this allows signaling to occur in less than a second after a notification is made. It also allows the company to see the pattern of notifications and exposures to see where hotspots might be, and this can be accomplished with aggregate analysis. So here's an example of using aggregate analysis to detect microclusters of COVID-19 as they emerge, and it shows the power of aggregate analysis. So the left-hand diagram shows you a chart in which the exposures and positive cases notified to the company are shown in real time, and this is recomputed every few seconds. It shows in this case that Florida has an outbreak, and so the managers realize there's an unusual problem in Florida in this hypothetical picture, and so they can do another aggregate analysis and continuously see which departments are having a problem. And it turns out it's in retail, as you see in the right-hand diagram, and so this is capturing the information for all 30,000 employees within a few seconds in both charts, and it shows that the retail has an issue and needs to be addressed by a change in policy. First, an immediate notification to the retail department in the Florida site, and then notification of action to be taken to limit the exposure. So you see the power of real-time digital twins to both provide fast notification and to provide aggregate analytics that helps make strategic decisions to deal with issues. So here's another example of tracking a power grid. This is another hypothetical example that we created as a simulation to demonstrate the scalability of the real-time digital twin model. And in this power grid, all these nodes are 20,000 nodes in this particular simulation. They represent zip codes around the United States, but they would typically represent power poles or controllers within that system. And so these nodes in the system can issue messages about their current state, their state of whether they're being attacked or whether there's a problem such as an overheating transformer that might predict a possibility of a fire. This could be especially important, obviously, in the forests where the power lines are running. And so by having this information, the real-time digital twins can derive a curated value for the level of concern. We could call it here an alert level, which is a derived value from this raw telemetry coming from all of these nodes in the power grid. And then aggregate analytics can give managers the data that they need to identify whether the problem is originating in one place or multiple places and how the problem is migrating. So if it's a forest fire that's migrating because of a burst transformer and is taking down other power poles, then you can see the direction and speed of the fire and direct emergency personnel and evacuations with very rapid response time by having this real-time aggregate analytics coupled together with the real-time telemetry handling of the digital twins. So how would you implement such a model of a real-time digital twin? We talked about it having two components, a state object, which is shown on the right there, and then a process messages method. They're both implemented by the application developer to handle telemetry from a single data source. And the streaming platform can then access the state object's properties in order to generate aggregate analytics. So let's look at some sample code just very quickly to get a feeling for the extent of it. And you can see here that this is a Java-based state object for the power grid example, showing you typical properties that might be maintained for this streaming application. The one that I put in bold here is the alert level, and this one is computed by the process messages code based on the telemetry in order to be aggregated using MapReduce to show where the problems are emerging and how important they are for this node relative to other nodes in the overall grid. So one of the things that we're seeing here is that we can, when we receive raw telemetry, for example, node condition towards the top is raw telemetry, and that comes in when this comes in, we can then update the counts and use these counts to create heuristics that allow us to generate this derived value called alert level in this sample. Note that you also can keep lists of messages or incidents that occur, say when a major incident occurs, keep an incident list. So this is all up to the application developer. So this is an example of a process messages method and written in Java. And you can see that it takes parameters or a context which has helper methods for sending messages and alerts. We don't need to talk about that today. And then the next thing is the actual digital twin object for that particular data source. And you can see it's provided immediately to this method, so there's no delay in retrieving it, and there's no work on the part of the application to retrieve it. And then lastly is a set of messages that can be iterated through that have been arrived from the endpoint, which could be Kafka, it could be an IoT hub, or it could be a REST service, and we could talk about that if there's time. So the key is that these messages are provided along with the state object, and then the code is simply going to step through the messages that have arrived and then implement application-specific logic that is appropriate for that particular situation. This is one example of a set of rules that could be written to deal with node conditions in the power grid. And what it just shows is that we're looking for deciding whether to raise the alert level based on whether or not we have a what is the current node condition. In this case, it's if it's a moderate incident, and also we're looking for how many false positives this node has already given us. And so if we've seen a lot of false positives, we're not going to raise this alert level. But if we haven't seen as many as other nodes, then we will raise this alert level. It shows how one could write a heuristic to set the alert level based on a variety of concerns that are particular to that particular type of a device or data source. You could imagine how one could write a predictive analytics algorithm for an engine or a refrigerator to fail based on looking at raw telemetry and then doing a predictive analytics computation to decide how high alert level to set to alert others that this particular device might fail, as one example. So that's the scope of the code. So the code only comprises a state object and a process messages method. The rest is hidden within the platform itself. So how do we actually run these things? They run within an in-memory data grid. An in-memory data grid is hosting the digital twin state objects as objects in the grid and scaling as necessary to handle the number of data sources that are present, in addition to providing data parallel analysis. So what is an in-memory data grid? I think we all in this conference have learned about in-memory data grids, but just quickly, it's typically implemented as an in-memory key value store for object-oriented data to give applications a global view of objects without concern about the number of servers and how the objects are distributed across servers. It typically has integrated high availability, and it often can include APIs for data parallel computing, which we can use for aggregate analytics here. And because of its ability to scale, it can deliver scalable high throughput while keeping the access times to the data and the response times to the data sources very low. So this is how one would run this problem of running real-time digital twins on an in-memory data grid as messages flow in. And this is shown slightly out of order, but you can see here the arrow pointing to the data grid where the objects are being held that represent the real-time digital twin instances for their corresponding data sources. And then another process on each server is called an IG worker, which is part of a worker grid, which is hosting the code that's running the message processing code, the process messages method defined by the application developer. And lastly, the connector grid is another process running on each server, which is talking to a message hub and receiving messages, hopefully in an optimized fashion, which can be done with Kafka, such that messages can be directed by the brokers directly to the IG connector processes so that the message is delivered locally to a local object. Or in some cases, it will have to be sent across the network to another object in the grid for processing. So you see that these three processes work in concert to deliver messages, run the process messages method, and then provide responses, alerts, and finally aggregate analytics. So some of the advantages we saw is transparent scaling, because we can process messages in parallel across all of the servers in the grid. And the grid is also ensuring reliable message delivery from the hub and also high availability for the stored data. So it also is reducing bottlenecks relative to the streaming pipeline we saw in the beginning, because of the fact that we're accessing data locally on the grid server, which is hosting the instance of the digital twin. What we're doing is essentially shipping the code to the data, or in this case, the message to the data where the code is running on all the servers. And by doing this, we are eliminating network transfers of data across the LAN and thereby improving scalable throughput. Note that we still, for high availability of stored data, we still have to do network transfers for replicating updates to state objects. So some of the benefits of this, of aggregate analytics, which can be incorporated into the real-time digital twin model, are that it can boost situational awareness. So we're going to talk for the rest of the talk about aggregate analytics and what its value is and how it helps boost situational awareness and how it's implemented within the grid. So real-time analytics can quickly pinpoint the sources that need attention, as we saw in those examples, and allow managers to craft strategies to respond to them. We saw this example of multiple points of intrusion, and we'll take a look now at a shortfall in hospital supplies. One could also imagine doing a reaction to an e-commerce flash sale and many, many other cases in which situational awareness is imperative for real-time intelligent monitoring. So here's an example of aggregate analytics for hospital supplies. You could imagine a scenario in which hospitals are sending to the cloud their current shortfall. Perhaps every minute they send a message to the cloud service describing which supplies are in shortfall, for example, PPE for COVID, and so that the cloud service can assess those needs relative to other hospitals. So the real-time digital twins can maintain this information about shortfall and curate that information to assess its relative importance compared to other hospitals and set an alert level for hospital supply shortages. And then aggregate analytics can run continuously to spot those regions that are having the highest shortfalls, and that allows managers to then go and query within a region to find the particular hospitals with their highest priority needs and what those needs specifically are, and then go address those needs. So you see that the real-time digital twins work in concert with aggregate analytics, which works in concert with query. Another example would be in health tracking. So you can imagine a scenario with many users of a health device like a Fitbit sending statistics to a cloud service. And again, the cloud service can curate the information it's getting based on knowledge about the person's medical history, their current medications, their age, their gender, the activity they're performing. And then aggregate analytics can look at all of the users, make some learn something about aggregate behaviors of populations. For example, that a new exercise that's being promoted at a exercise center is causing high heart rates in certain individuals, and then provide that feedback so it can be provided back to the users. So aggregate analytics can also be used in a feedback loop with responses to the users of the real-time digital twins. This gives much faster responsiveness than the use of a data lake. So how are aggregate analytics integrated into real-time digital twins? And this is really the core of what we're trying to communicate in this talk. So you can think of the real-time digital twin state objects as hosting properties, as we saw before. And so the user of aggregate analytics can select a property to aggregate for a MapReduce computation. We'll look at that in a minute, and select another property to group the aggregated values by. So one could look at alert level by region, for example, and by simply selecting properties out of the state objects and allowing the platform then to perform a MapReduce, which is aggregating data in groups, then these results can be produced very, very quickly. And the key thing is that they're leveraging the state values within the real-time digital twin instances, which is essentially providing a domain for data parallel computation, as opposed to sending all of the data out to a data lake and then having batch processing identify the domain and go select the data out of a large data lake of telemetry data and figure out what is interesting and to get that result much, much later. So what is MapReduce? I think we've seen MapReduce going back to the days of Hadoop, but just very quickly, MapReduce has two phases. The first phase is the mapping phase, in which all of the raw data, in this case, the selected property from all of the real-time digital twin instances, is then mapped according to the group. So the mappers, of knowing the groups, will in parallel split up the source data by group and then feed that to the reducers to do the actual aggregation. So if you're trying to find the max alert level by region, the mappers will simply take all of the input data from the power grid nodes, for example, break it up by region, and hand that to a separate computation, which is aggregating it by region, and then providing a set of results, one result per region. And these results can be performed in parallel on each server within an in-memory data grid, and then the results can be merged and combined and delivered for visualization after being merged across all the hosts or the servers in the grid. So there's two ways we can think about doing this. One way to implement the MapReduce is to run it within the worker process that we saw before that's executing the real-time digital twin model. Notice this worker process is a client cache, which speeds up access to the state objects for reading purposes. So this allows us to implement MapReduce in Java if we're running a Java virtual machine, or .NET, or in C# if we're running a .NET runtime. The problem or the limitation is that it requires the state data for all of the instances to be communicated across a connection, an IPC connection, between the data grid server process and the IG worker process. And this can impact overall scalable throughput and create more overhead, typically CPU overhead for the server. So another way to do this is to run it within the server process where the data is held itself, the data grid, instead of in the IG worker grid. And by doing this, we can eliminate the data transfer through IPC and give us the best combination of throughput and completion time. The restriction that is imposed here is that the server has to understand the serialization format for the state objects. So if we can agree on a format like JSON, then the server can extract the interesting properties for the mappers and for the group by from all the state objects, perform the MapReduce, and return the result. So now I'm going to try to give you a little demo of this. First, I'll tell you what you're going to see. We're going to see the creation of a widget in which we select, as shown on the left-hand side here, we're going to select the state field, in this case alert level, and the aggregation operator and the group by field. And then hopefully we'll see a chart of this aggregating in real time. So this is an image of our real-time streaming service. It's called the ScaleOut Digital Twin Streaming Service. And this is not meant to be a product briefing. It's meant to be a technical briefing. But just to show you, there's 20,000 instances running for this simulated power grid. Here's a simulation of the power grid. This is showing the workload generator, which is having these 20,000 nodes running. You might see a twinkle, and they are emitting messages that we're depicting in one of these colors. These are not meant to be directly believed by the real-time digital twins. They're simply meant to be an indication of what the node thinks its current state is. And some nodes will have false positives. Other nodes, may go offline or just generate erratic data. So we want the heuristics in the twin to filter out the actual erratic messages and provide a more authentic view of the state of the nodes. And that's an example of creating derived state for the managers to aggregate. And so the derived state we're interested in here is the alert level. So we can go look at a dashboard here. And this is the running real aggregate analytics based on a widget. And this widget is defined by creating a new widget by selecting the type of chart, the namespace or the type of digital twin model to be run, and then we can select a state field here, and there are many state fields. We chose alert level in this example, and then we can also look at the various aggregation operators, and then next select a group by field. In this case, the group by field is the region, as we were talking about earlier. And then finally, this has already been created. You can see it running. And so every few seconds, it's recomputing for the 20,000 nodes, the maximum alert level by each of these regions. So we can go back to this chart here and create an incident, hopefully. So this will make this thing very unhappy, because there's some nodes are now going to be having a problem. And we don't know where they are because we're a manager of this grid. We're just watching this, and we see, okay, there's two regions that have had a problem now. And so we can now, here's 3 regions. So we see the problem has been evolving, and now we can go and use query and understand, well, what's going on. We know the Northwest region is having a problem, so we can construct a query, select the state properties within This is within the digital twin state objects. These are the properties that we just saw in the code sample, and we can run a query to see, well, what's going on and get the latest information about where the incidents are occurring. And we can see where the severe incidents are. So we see that this node here has a higher severe incident counts than the others. We also could show the alert level here, so which would be more interesting. Not shown in this one, so let's do that. Let's add that in and see the alert levels and see which. So this thing is probably now returned back to normal. And let's go back and create another problem. And so we can see in the dashboard, if a problem occurs, then we can do something to find out where it's occurring and what it is. So waiting for a problem, there it is. 3 nodes will go back to northwest again. And so we'll go back to the query and query this. And then we can see where the alert level has jumped. And there we go. There's a node. This can be sorted by alert right here. And you can see where the problems are severe. So these nodes are having a severe issue, and we can now go find out, make phone calls, do what we need to do to address that issue. Okay, so let me just jump back into the talk for a minute. So just to wrap up, some of the takeaways from this discussion today are that for the real-time digital twin software model is enabling streaming analytics to expand its current uses to track large numbers of data sources for intelligent real-time monitoring. And it's offering several advantages over some of the more traditional techniques that are pipeline because of the fact that it's making state information about the data source a first-class citizen of the model. So it's including context-based introspection based on the state information, which deepens the introspection, while at the same time simplifying the application design, because the application developer is now focusing on introspecting on telemetry from a single data source and not from worrying about extracting data out of an aggregated data stream of incoming messages. It's also, and importantly, providing a domain for aggregate analytics by using the properties in the state objects. So the real-time digital twins are surfacing a domain for analytics as opposed to not providing a domain and having offline systems have to construct a domain in order to do the analytics. And it also then allows that analytics to be performed in real time on live data to give very, very fast results and maximize situational awareness. This is all made possible by mapping this model to in-memory data grids, which allow the model to transparently scale and allow it to implement real-time aggregate analytics while avoiding data motion. And this gives the best possible throughput and response times in milliseconds and aggregate analytics in seconds with the lowest possible CPU usage and network usage, and thereby giving the users of the system the best picture, current picture of the evolving situations and the best possible situational awareness. So that's the talk for today, and I hope you enjoyed it, and let me know if there are any questions.
Hey audience, if you have any questions for Bill, post them in the questions panel. Bill, one thing that came up earlier was how does this compare to the Azure PaaS service? Are they similar to each other? Are they like complementary? How would you compare them?
If you're referring to Azure Stream Analytics, that Azure Stream Analytics, again, is an example of a pipeline system looking at the stream of telemetry coming in from an IoT hub and trying to view it as columnar data and extract patterns of interest out of that column of data. What's unique about this approach is the tracking of state for every data source, and only a model which has a twin to every data source is going to be able to allow you to keep contextual information for every particular data source. We saw the Swim AI yesterday is a very similar model. That was a very good talk. I highly recommend you see Simon Crosby's talk from yesterday. And it's slightly different than this. It's also I would call it a digital twin model. Simon may not, but what's different is that it also incorporates nearest neighbor access to state. And so for geospatial problems, it's useful to see the state beyond just the particular data source, but of the data sources that are in the surrounding area. But in both these cases, there's state information about the particular data sources that is being analyzed by the streaming analytics system. And that's what really makes this different than most streaming analytics platforms that you'll see, like Azure Stream Analytics.
Yeah, Simon is agreeing with you.
Okay.
He's in the chat there, so. And I mean, he had this, you may cover this, but let me, throw this out anyway. How do you surface the schema? That is, what can you map and reduce against if you're a random user?
You map and reduce against the properties of the state object, as we saw in the demo. You select the an interesting property. Typically, these properties have been derived from the telemetry. They don't represent the raw telemetry. Like alert level is a derived property, but any property that the state object is hosting can be extracted for aggregation with the aggregate analytics, and any other property can be used for the group by aspect of MapReduce. Some properties are useful, some would not be. Properties that would have, for group by, that have thousands of values would not be particularly useful. But those that have tens of values, like region or state or hospital name, could be useful.
Very cool. I think that brings us to the end of this presentation. Bill, did you have any closing comments?
I just want to thank you all for attending, and hope you're enjoying the conference. And I want to also thank GridGain for hosting this conference, as they've done for several years. I think it's a great service to our community of in-memory computing users. So thank you very much.
Awesome. Thanks, Bill.